When you type a prompt into a standard centralized AI interface, you are paying for the service with your own data. Every query, code snippet, and confidential strategy you submit routes directly into a corporate server, logged and used as training data for future models. OpenAI's Enterprise Privacy page is 2,400 words long, explicitly detailing how data moves through their infrastructure. That page exists because corporate legal teams forced the issue after high-profile leaks, like Samsung employees inadvertently sharing proprietary source code and Amazon staff pasting confidential documents into chatbots. Centralized providers now offer settings that supposedly opt you out of training, but those are mere software toggles on someone else's hardware. They provide zero architectural protection when the next major data breach occurs or a government subpoena arrives. Privacy in AI is defined by sovereignty. When you run inference on infrastructure you control, your data exists strictly on your own terms. For an enterprise, funneling workflows into a centralized API is functionally identical to storing proprietary business logic on an unauthorized third-party server. Despite the clear risks, most engineers assume the alternatives are unworkable. The default industry consensus is that securing AI data through decentralized networks requires massive latency penalties and prohibitive costs. To test that assumption, we need to evaluate the cryptographic technologies available today, the reality of enterprise compliance, and the raw unit economics. Clarifying these costs is essential. The false belief in an AI privacy premium is the main bottleneck preventing widespread AI enterprise adoption. Three distinct cryptographic approaches dominate the conversation around securing private AI inference. This chart plots the computational overhead required for each privacy technology compared to a standard baseline. First is fully homomorphic encryption, or FHE. It allows computation on encrypted data without ever decrypting it, which is mathematically brilliant but currently unusable for AI. As the chart shows, FHE imposes a massive 100 to 1,000 times compute overhead. Next is multi-party computation, which splits your prompt into fragments processed by different nodes. This avoids centralizing the data, but it adds a 10 to 100 times latency penalty due to the constant network coordination required between parties. For processing a single prompt, that is heavy overkill. That leaves trusted execution environments, or TEE. As you can see, TEE operates with near-native performance, registering less than a 5% overhead penalty. A TEE physically isolates processing inside a hardware-enforced enclave. Your encrypted data enters this secure boundary on the GPU, decrypts locally, processes the AI inference, and encrypts again before leaving. Not even the server operator can view the contents. This architecture does require a specific trade-off. You are swapping trust in a broad cloud provider for trust in the specific hardware manufacturers, like Intel or NVIDIA, who build the chips. Hardware vulnerabilities do happen, like the Intel SGX extraction attacks in recent years, which required coordinated key updates to fix. But even with those hardware trust factors, TEE remains the only mathematically backed privacy protocol capable of sustaining the speed and throughput needed for enterprise-grade AI production today. At the same time, expanding regulatory frameworks like GDPR, HIPAA, and the EU AI Act are forcing corporate legal teams to restrict employee access to centralized chatbots. The problem is that many organizations confuse legal compliance with actual data privacy. Signing a business associate agreement, or BAA, with a major tech company is just a legal contract. It dictates terms of use, but it does not physically stop your data from being processed on their external infrastructure, nor does it protect your data from surviving a government subpoena. Running inference on a decentralized network using TEE hardware simplifies this equation. Because the host never has the keys to decrypt your prompt outside the hardware enclave, your raw data never physically resides on third-party controlled storage. By using cryptographic data routing, you ensure external parties cannot be compelled to produce records they never possessed. It turns a complex legal liability into a solved engineering problem. This infrastructure is actively functioning at scale right now. The privacy-focused inference platform Venice processes over 45 billion tokens daily across 1.3 million users. Venice achieves this by bypassing centralized servers entirely. It proxies prompts to a distributed network of GPU providers sourced from infrastructure projects like Akash, NEAR, and Phala network. They recently deployed an end-to-end encryption pipeline to secure this process. When you type a prompt, it is encrypted locally right in your browser. That locked data travels across the network and only unlocks once it is safely inside the hardware enclave of the target GPU. This provides a strict cryptographic guarantee. Neither the routing proxy nor the underlying GPU provider ever has the ability to read your prompt. And networks like Phala are backing this up by providing verified TEE hardware that holds SOC2 and HIPAA compliance certifications, establishing a clear standard for enterprise usage. This chart compares the unit economics of these private networks against centralized equivalents. Venice provides access to budget models for 7 cents per million tokens. By contrast, OpenAI charges $1.75 per million tokens for similar baseline capabilities. Decentralized network economics utilize reverse auctions to drive the cost of private compute down. The higher price you pay to centralized APIs covers brand margins and corporate infrastructure overhead. This matrix plots deployment against data sensitivity. First, local inference on your hardware is the gold standard for highly confidential data. Next, TEE compute is ideal for cloud-level quality requiring cryptographic sovereignty. Conversely, centralized APIs should be used only for public data demanding frontier model capabilities. Not every single workflow demands strict isolation, but architects must ensure the infrastructure layer aligns with the specific risk profile of the data. The current market operates on a flawed assumption. It incorrectly assumes that keeping your proprietary data secure inherently costs more money. When you supply centralized providers with valuable training data, usage patterns, and competitive intelligence, you are providing them with a highly valuable asset. That exchange should earn you a discount rather than costing you a premium. The shift toward decentralized, privacy-focused infrastructure addresses the specific compliance pressures that make centralized models a liability for regulated industries. The decentralized networks capturing this enterprise adoption are the ones deploying practical TEE hardware today, actively solving immediate compliance bottlenecks long before technologies like fully homomorphic encryption reach maturity. Privacy in AI is essential because every prompt you send to a centralized provider is a calculated liability you are choosing to absorb. Decentralized compute networks flip that equation, providing cryptographic guarantees at a fraction of the cost.